I don't think he really needs an introduction. So, Alex.
All right. It's good to see everyone who I recognize from the SF Video Meetup, and it's great to see the new faces here. I'm Alex Converse. I'm a software engineer at Google on the WebM video coding team, and I'm presenting the things that we are doing in VP10 so far to try to help make your videos smaller for distribution. The work I'm presenting mostly is the work of my teammates whose names are over at the side and not my own. It's really a group effort here. So the WebM project started in 2010 to develop royalty-free codecs. It was started by the Google acquisition of On2. We launched VP8 in 2010. That didn't have a lot of success for video on demand content, but it's been really great in WebRTC. And we launched VP9 in 2013, which YouTube seems pretty happy with so far. The typical recipe for a new video codec is you release one every 10 years, sort of based on a hardware cycle. And really that's based on a hardware cycle for the broadcast industry and for sort of optical disc boxes and that sort of thing. And we think that's a little bit out of date on the internet. We have rapidly rising demands for resolution, frame rate, dynamic range, and quality within those constraints as well. So we need to innovate faster. So our main goals for VP10 are to improve the core performance of the codec. We want to get smaller file sizes. We want a whole 50% bitrate reduction generation on top of VP9. We care about every video resolution, not just HD, not just UHD. It always sounds impressive when you say, I'm making a 16K codec, but the truth is that's really easy. You just put in enormous transform sizes, and that does like half the work for you. Innovating at the smaller resolutions can actually be a lot trickier sometimes. We want to keep the decoder complexity bounded. It's really important for us to be able to do software decode of 1080p 60 content. We also want to help try to support new applications when possible. We want better support for screens and gaming content. We also are interested in doing anything we can do to make our codec more friendly for light fields and virtual reality. And we want to do this all within about 3 years, and not really 3 years from now, like 3 years from a year ago. And then this whole Alliance for Open Media thing happened. You may have heard about this in the news. A whole bunch of companies got together, and we want to produce one royalty-free codec from all of the great technology that we've been individually working on. We want to take the best parts of VP9 and VP10 and Cisco's Thor codec and Mozilla's Dala codec and any of the technology that the other members have and combine them into one really, really awesome codec. This is all very new, though, so what I'm really presenting is the work that we've done on our own in the VP10 world that we're going to bring to the Alliance. So not everyone here works in codecs all the time, sadly. I don't know how you can not want to rage quit your jobs when you're stuck working outside the codec. But so a quick overview of how image and video coding sort of works is you take your image, you chop it up into blocks, generally by overlaying a grid onto it. And then for each block, you predict the blocks from the blocks you've already processed. You subtract the prediction from the block you're trying to code. You take some sort of DCT type transform of the error, and then you do some sort of entropy coding on the DCT tokens. At the bottom, I sort of have an example of spatial prediction, where you're using the previously coded pixels and projecting those downwards at a 135-degree angle, we call that. And I have the DCT basis functions on the right, which sort of captures what the low energy, easier to code things are towards the top left. And then we're not just interested in pictures, obviously. We're a video codec. So the big thing about video is motion. Most of the contents of your current frame are already in your previous frame. Sometimes they're just in a different place. So you can use the previous frame to predict the current frame. You can assign motion to each block and use that as your predictor instead of the spatial prediction. Since video is generally operating at lower bit rates, you get artifacts from this. So you can have You can have filters to remove these artifacts, and you put that in your processing loop to keep artifacts from propagating forward. All right, and VP9 does a couple of things that aren't necessarily trivial from sort of the release in a nutshell codec. We have the DCT transform, which I mentioned before, and we also have a single-sided transform, which is represented at the bottom of the frame, where the idea is all of the energy is on one side of the transform. That can be useful for when you have really strong prediction coming in from one direction, and you're really only interested in updating the sort of faraway edges from it. We have scalable reference frames, so for hard content, within a single video, you can drop down to a lower resolution, and then when things get simple again, you can pop back up, and the codec can handle prediction across those seamlessly. You don't need to do a new keyframe and lose all of your time prediction. So we have a variable prediction size. We don't just divide the codec into 8x8 blocks. We start with 64x64 blocks, and then sort of recursively partition that down to 8x8 or to 4x4 for some information. And transform sizes, we do 32 by 32 transform for spatially simple areas, and we do 4 by 4 transforms for really complex things, and we do all the powers of 2 in between. We have multiple filters for fractional pixel motion, depending on if you want smooth or sharp. We support special transforms for lossless coding, and we context everything on something. That's just a fancy way of saying that you use what you've already coded, not just the pixels, but sort of the description of them. Like if you say, I'm coding a strong horizontal pattern here, then when you move horizontally to the next block, there's high chances that you're going to continue with your strong horizontal pattern. All right, so in VP10, we're interested in doing brand new things and also trying to combine the things we already have in a richer way. We're pretty much every part of the codec we're interested in reevaluating and taking a new look at. We're not trying to make this sort of an extension on VP9 where someone can reuse 75% of their existing VP9 codec to make a VP10 codec. If it has big gains, we're willing to tear it up and throw it out and replace it with something new. And nothing I'm presenting is set in stone. This is all just a snapshot of today. Some of these ideas may be too complex or not workable. Some of them we may just come up with better things that replace what we're currently playing with. And a lot of challenging work lies ahead. VP10 definitely isn't done. So one of the first things we started looking at was high bit depth internal support for VP10. We added this to VP9 sort of late in the cycle in what we call Profile 2. Having high bit depth buffers offers a big compression advantage even for 8-bit content. Coding an 8-bit video with 10-bit or 12-bit buffers gives you 3 to 5% compression gain. Basically, the way this works is that you're not accumulating rounding errors constantly. If you add 2 8-bit numbers, you get a 9-bit number, and you have to stop and round. You multiply 2 8-bit numbers, and you have a 16-bit number, and you have to stop and round. If you can keep all the rounding errors to low bits that get discarded before display, you can preserve a lot of extra quality. So this is an optional feature in VP9. So it's not completely new, but we're talking about making this either mandatory or default in VP10. So we're expanding our partition structure in VP10. I kind of talked about this in the overview of VP9, where VP9 uses a 64 by 64 block structure and then decomposes that all the way down to 8x8 into 4x4. It also supports, beyond just 4-way split, horizontal and vertical splits for sort of large but not square areas. In VP10, we've added these T-shaped partitions. We have both recursive and non-recursive versions of the squares in those. We're not quite sure which one we're going to use. We're also looking at raising the base size of our quad tree, what we're starting with, from 64 by 64 blocks to 128 by 128 blocks, which has advantages for HD and 4K. So another thing we've been looking at is something we call filter intra-prediction, which is rather than doing traditional spatial interprediction where you're dragging pixels in a particular direction, what you do is You can define these filters and apply them pixel by pixel from your already coded pixels, working across and down the frame. And you apply this process recursively. And if there's interesting spatial content on your border pixels, the filter will propagate interesting spatial content in what you're trying to predict. And this is a collaboration with UCSB, one of the outside groups that's giving input into VP10. So another thing we're looking at is enhancing interprediction, which is your prediction between different frames. In VP9, for a given frame, you get to pick 3 reference frames you want to use from a pool of up to 8 buffers. And then for a given block, you pick either 1 or 2 reference frames and 1 motion vector for each reference you use. So in VP10, we're looking at increasing the number of reference frames, a frame you're trying to code, to 5 or 6. This can give big gains, especially in uncovered areas, whereas something is moving around and you need to backfill whatever was behind it. So we have new ways to do single references in a block with all these extra frames, and we have more advanced ways to combine 2 frames together. In VP9, if you're doing 2 reference frames or 2 references on a block, you do motion from one reference, you do motion from the other reference, and then you just kind of average them 50-50 across the whole block uniformly. So one thing you can do is combine interprediction, that's prediction from motion again, with intra-prediction, which is the spatial prediction. This is good where in a block you have sort of the edges of your motion. You generally have strong intra-correlation along the edges, and that gets weaker and weaker as you move away from the edges that you've already coded, which is a great place to replace that with motion prediction. In this case, the weights smoothly vary. It's like a diagonal crossfade here because you're using a diagonal predictor. So another thing we're looking at is wedge partitioning. Unfortunately, in video, not all moving objects are rectangles. It would be really, really great if they could be. Like if you can replace all your actors with rectangles, that would be amazing. Typically, codecs handle this by dropping down to smaller block and smaller transform sizes on the edges. And this turns out, and this can be in certain cases, really inefficient as you go along a complex edge where you really just have 2 zones and you're being redundant. And if you're being redundant, you're wasting bits. So one thing we're looking at in VP10 is to allow oblique partitions to go through a block. This is sort of an extension to the quad tree partitioning, where once you get to the end, either your square or rectangle, you say, all right, now do I have a diagonal line dividing this block? So we call a set of sort of candidate lines through a block a wedge codebook. These are sort of, the wedge codebooks are sort of a property of the format. This allows you to just send one number, the index of the line you're using in the bit stream. So you send one wedge codebook index, which is your line, and you send 2 predictors, 1 for each side of the wedge. The predictors are combined with what we call a cliff weighting scheme. It's not 100% to 0%, but it's much faster than the smooth weighting from the previous slide. And along the wedge boundary, we're doing overlapped motion compensation, which is something that some implementers love the complexity of, let's say. So we can do wedge for 2 interpredictors or 1 inter and 1 intra. It pretty much works the same, conceptually the same way. It's just whether or not your second predictor is inter or intra. So another thing we're looking at is global motion. The current generation of video codecs all use a translational motion model where things basically are moving in 2 dimensions. But we know that pans and zooms and motion in gaming and all that stuff is actually really common in videos. So there's a bunch of different models of increasing complexity you can use for global motion. What we're sort of doing is using this to warp the prediction, so our 0 motion becomes 0 motion relative to your global motion. There's ongoing work to be able to compute this better and more reliably. Now, I kind of weaseled out at the top and I said the current generation of codecs use global motion. You know, some of you may remember that like MPEG-4 Part 2 used global motion and it wasn't really that successful. We think it merits sort of a re-examination in a world where GPUs are ubiquitous and sort of trying to compute to pre-warp pictures and things like that becomes a lot cheaper than it used to be back in the MPEG-4 generation. So kind of a summary of all of the new prediction tools in VP10. We have the 5 references you get to pick from again. On this slide, the gray text is stuff from VP9. The blue stuff is all new VP10 stuff. And the red stuff is stuff that's removed because it's now redundant with the blue stuff. So, I mean, we've more than doubled the number of ways you can do prediction in VP10. So, another thing we're looking at is something we call super transform. This is actually not just a new way of looking at the transform, but a combination of prediction in the transform. In VP9, you walk down your quad-tree partition structure and get to a certain size, and then you're allowed to pick any of the transform sizes of that size or smaller. So if you're doing a 16 by 16 block in VP9, you can do a 16 by 16 transform, you can do an 8 by 8 transform, or you can do a 4 by 4 transform. But what if you could do a transform bigger than that? What if you could combine multiple prediction blocks with one transform? To do this well and to prevent artifacts, you have to do filtering before you apply your transform error. And that essentially makes this now recursive overlapped block motion prediction underneath your larger transform. So besides super transform, other things we're looking at with the transform is in VP9 for motion, we use DCT exclusively, and we use that ADST for intra-prediction. In VP10, we're allowing the ADST for motion and also the symmetric DST, where all your energy is in the middle instead of the edge, and the flipped ADST, where all of your information is on the left edge instead of the right edge. So you apply that over a 2-dimensional transform, and you have 16 different transforms to choose from for every block. We only find this really works up to 16 by 16, and then it kind of falls apart for bigger stuff. So we're investigating alternative transforms for bigger sizes. VP9 has a 32 by 32 DCT. We're looking at 64 by 64 transforms as well. We're looking at wavelet DCT hybrid transforms. And I recognize the irony that a couple months ago, I told a bunch of you that wavelets are dead. So copy mode is something else we have where you can copy sort of the entire set of motion information, not just the direction of motion, but the references you're using and the filtering and sort of the information that goes along with that from a neighboring block. You're basically sending the index of a neighbor rather than whole new motion information. This has a strong overlap with the way we already propagate motion through a frame in VP9, and that still needs to be resolved. In VP9, generally, when you're trying to figure out the motion for a block, you start by looking above and use that, or you can instead say, no, I want to go to the left and use that. And if there isn't an above and a left, then you go to previous frames. In this scheme, there's left and above, and there's other options as well. So filtering. VP9 has a deblocking filter that's done both on the encoder and decoder so that you have cleaned up reference frames so that block artifacts aren't propagating. In VP10, we're looking at adding a nonlinear filter to reduce other classifications of artifacts as well. We have a couple different experiments. We have a bilateral filter and an adaptive Wiener filter that we're both still playing with. So, and some smaller things that don't really fall into the buckets, or actually some of these are quite big ideas, is, big transforms again. 64 by 64, we've only seen small gains so far, but we're playing with non-DCT transforms. We know the Cisco folks are very enthusiastic about their 64 by 64 transform. We're looking at super resolution, which is a concept where you scale a block, or you code a block at low resolution, and then you use some sort of data-dependent filter to upscale and sharpen it. And we're looking at offering sort of tile-based random access where you can have strong random access properties to just a part of the picture to aid with VR and light field type applications. So we're also adding new tools for coding screen content. VP8 currently still powers Chrome Remote Desktop, and we really want to have a huge generational improvement for screen coding. Screen content generally contains lots of text and graphics. This slide is sort of a perfect example of screen content. Conventional coding tools try to compact the energy of smooth things into low frequencies, but the side effect of that is that sharp things get scattered out, and they're not so great for coding sharp edges and very intricate sharp patterns. And even in real-world non-screen content videos, there's often elements of screen content. There are things like watermarks and overlay graphics and tickers on video, and even things like having letterboxing burnt into your video. Some of the screen content tools can help handle those situations better. So one thing we're looking at is palette coding for cases where you have complex patterns but very fixed number of colors. Things like the Google logo up there are perfect examples of things you'd want to code with a palette. So you can use, so in palette coding you have to have your palette that you're sending and then the indexes into the palette that you're using for a given pixel. The palette can be computed with the k-means clustering algorithm we're currently using. It's just a really nice algorithm for clustering groups of things together. So then we transmit the colors used in the palette in the bit stream. We keep a rolling list of colors in the, at the frame level to remove the redundancy of having to recode colors constantly. And we context the neighbors, we context the pixel we're currently coding on sort of the 4 adjacent neighbors. Traditional palette codecs have sort of done run length type encoding, but we find this contexting scheme gives us pretty big gains. And we do this instead, we do this whole palette thing instead of the traditional intra prediction, the sort of dragging the pixels. So another thing we're looking at is getting rid of the transform for some blocks, obviously, not for the whole codec. Transform coding, like I said, compacts sort of smooth things into low energies, but isn't great with sharp things. I have a diagram over to the side that says DCT is so great with some ringing. It looks way worse on this screen. The projector kind of washes it out. But you've all seen pictures with way too much JPEG applied to the text. And non-transform coding is great for that. And it opens up new ways you can handle your prediction. So traditionally, you predict the whole block, and then you take the reverse transform of the whole block, and you add those together. But when you're not doing the transform, you can sort of grab your coded error signal 1 pixel at a time, add that to your prediction, and then use that to predict the next pixel. We do this for horizontal and vertical prediction and something we call true motion, which is sort of a superposition of horizontal and vertical. The diagonal prediction angles use complex filtering, so we're not using this here. Another thing we're looking at is block displacement within a frame, right? Your P frames in video are generally your smallest frames because most of the information is in the previous frame. But if you're halfway through coding a frame, through coding a new keyframe, you already have half a frame buffer available for you to use. So we basically let you use that as a reference for motion style prediction, where you can point a vector back to somewhere in the frame that you've already coded and copy data from there. It's great for repeated patterns, repeated textures, for text, all of those sorts of things. So results so far. On low resolution videos, VP9 and HEVC only see about a 14% rate reduction compared to 264. Like I said, low resolution is really tricky. For VP10 8-bit, we're seeing an 8% reduction so far, and we're already up to 12% with VP10 12-bit. For medium resolution, VP9 and HEVC see about a 30% decrease. Most of the VP9 HEVC gain is really at HD resolutions. And we're seeing 12 to 14% reduction in VP10 thus so far. And for screen material, we're seeing 20% reduction because VP9 doesn't really attempt to intelligently handle screen content at all. So those gains were really easy. So we think we've made some substantial progress towards a new codec, but obviously we still need a lot of work to get to 50%. We definitely need a few new big ideas and not just to tweak the things that I've already presented. Everybody's welcome to join. All the development's in the open. You can join our mailing list. You can look at our project on GitHub. To be honest, the mailing list is kind of quiet, and most of the interesting discussion actually happens in the patch tracker. But if you sort of navigate through the GitHub link to our homepage, you can find a link to the patch tracker where people upload and discuss patches. So that's it. Thanks.